Welcome back to the historic steelworking town of Söderfors in Sweden. Today we are visiting Eersteel. We are going to learn about how they make high-speed steel. High-speed steel is the steel that you make drill bits and gear cutters and machine tooling and all sorts of aerospace parts from, and it can't be made in conventional steel-making ways. We're going to learn about how Eersteel makes steel powder with a process that was developed here in the 60s and has been refined since then. I'm going to learn about how they transform that into their incredibly highly alloyed steels using their hot isostatic pressing technology. I cannot wait to get stuck in. It starts with the raw materials that here are almost entirely recycled scrap. So when the scrap comes in, it is sorted by what it is. And they can use these portable XRF devices to actually scan the material and get an exact chemical composition and find out what grade it is. Eersteel is usually making super highly alloyed material, and so of course, they'll sometimes need things like this, pure cobalt scrap. Occasionally they'll have unused powder from their processes that makes it in scrap, their own internal offcuts from the forging line, and there's scrap milling chips from machine shops, as well as these ginormous ingots of the known scrap content, in addition to broken end mills and gear cutters and drill bits of high-speed steel. And then it is on to the induction melter. This represents the material for one melt, which happens up there. Hi, Victor.
Hi, Alec.
How are you?
Good. Welcome to Söderfors in Eersteel.
I'm so thrilled to be here. Yeah. What is this?
So this is Durin, one of our two atomization towers here in Söderfors.
And am I right in understanding that that's the biggest in the world?
Yes, so we host the largest capacity for metal powder production in the world, and we have two of the largest atomizers in the world here in Söderfors.
And so what we're going to see is we're going to see how all of that scrap gets transformed into a perfect steel powder of the perfect chemical composition in every single grain.
Correct.
Jamie, you can't be recording in here. Up we go. So this is the control room. So this is where, you know, all the parameters for the induction melter are set and calibrated and monitored.
So right now they're melting one heat in the induction furnace that will be poured and transferred to the atomization tower.
This control room is at the top of that big concrete building that we were just outside. And it's kind of an interesting perspective. It feels like you're at ground level, but actually we're like 20 meters off the ground and the atomization tower is underneath us.
Correct. So we took an elevator 6 stories up and everything is below us.
And we can go see from in there?
Yeah. All right. Here we go.
Wow.
So they're trying to bring the melt up to temperature now.
How hot does this need to be?
So 1600 Celsius basically.
Wow.
Yeah.
That is screaming hot.
So the liquid steel is just being heated up and getting to the correct chemistry inside the induction furnace. It doesn't have anything to do with the atomization process itself. It's just preparing the steel for the atomization process.
That ongoing analysis and calibration of the melt, that's happening right here.
So they're taking out small scoops of liquid steel that solidify into mini ingots, and then they prepare those ingots and they run analysis in our laboratory right next door.
They get an analysis, they come back, they shovel different material in to change it.
Exactly, and we can go around actually and have a look at those elements.
Nitro vanadium.
Yeah, so if you need more nitrogen, you need more vanadium, you have that. You have cobalt here that you saw earlier in the scrapyard.
Ferrovanadium. Oh my goodness.
So these are more, let's say, virgin raw material coming out of the ground.
Yeah.
So this is ferroalloying elements.
And this can't be scrap.
No, so this is what we try to avoid using because it's very expensive and it's, it's not that good for the environment. We want to use as much scrap as possible.
Yeah.
So typically we aim for around 95% scrap and the 5% ferroalloying elements.
So in order to dial things in precisely, you sometimes have to get the exact alloying element, and it just can't be scrap.
If you're low on vanadium, you take a shovel of ferrovanadium and you throw that into the induction furnace to balance out the chemistry.
Oh, and look at this! Here, in Söderfors, you have, I presume and I hope, a Söderfors anvil. Because Söderfors, that name is famous all over the world for a very, very high quality anvil. And do you know who is famous around the world for high quality underwear? Well, that, my friends, is today's delightful sponsor, MeUndies. We're thrilled that they're back supporting the channel for another year. And over the previous year of wearing MeUndies, I have been so happy because their stretchy micromodal fabric is oh so soft, light and comfortable. It's breathable, and it is truly the comfiest underwear that I have ever worn. And I'm quite picky about these things. From the mountains of the French Alps to the forests of rural Sweden, and in my own, sometimes sweaty workshop, MeUndies has been there with me. And just in time for Valentine's Day, you absolutely need to check out their incredible Valentine's Day range. Look at that, penguins in love. Go get matching underwear for you and your partner at meundies.com/forge, because their collection has awesome prints made for two. And when you go to my link, meundies.com/forge, and use our promo code FORGE, you can save up to 50% off. Let's get back to Eersteel. So the whole induction furnace is now tilting that 10-ton pour. Oh yes. That is a 5-inch stream of molten steel. That is so much material being poured. These things just make me so happy. You know, some real caveman instincts in me. I see fire, I see hot things, I love it. The induction furnace has been completely emptied. It is 90 degrees. And so now the ladle gets transferred to the ton dish. Yep. Where it can then be tapped for the molten steel to be turned into powder.
Correct, correct.
The lid is now off the induction furnace and they're loading the next heat with another batch of scrap that's been brought up to the top of this tower.
Yeah, so in the paper bags it's graphite, so for getting carbon into the melt.
Amazing.
Bags of graphite.
Oh, so this is the mix of new alloys being poured in. Yeah, that includes bags of graphite to increase the carbon percentage.
So this is more raw material, virgin raw material, let's say, and the rest will be scrap.
See, that's an incredible... Oh my goodness, that makes me so happy. How long does it take to bring a full load, roughly, up to melting temperature? 4 or 5 hours?
Yep.
That is incredible.
All right, so this is the chemistry lab.
And this is right next to
the control room.
The control room, the other side of the control room in the Atomization tower here. And so this is, we described earlier, they take a ladle of the molten steel as the melt is developing. They bring it into here, it cools down and it's tested while that batch is still going.
Exactly, so the first step is to cut the small ingot into a sizable piece that you can use for analysis. Then we have several steps of grinding and polishing to get the correct surface finish on the sample.
And that has to happen right then?
Yeah, so it's very time critical.
In minutes?
Yeah, it's very time critical. They check both on these type of samples, the XRF, we can go over and have a look at it. But what they also check is with these type of equipment, the LECO equipment, they check for elements that cannot be picked up with an X-ray. So carbon, sulfur, oxygen, nitrogen, very light elements you cannot analyze with an X-ray. So in these type of equipments, you heat up a small, either we can take powder or you can basically crush up a piece of steel. And it combusts it, and it uses IR spectroscopy to analyze the content of that steel. So these are the XRFs. So you have polished steel samples. They go into these holders, into this tray, and it's brought into the machine, and it checks. So you run it against a known standard, so you know what grade you're trying to produce, and it compares the results from the sample that you got from the guys out on the shop floor and the known reference, and you see, okay, we need to add a bit more of this element to get it correctly. And
so this is the lab scale and grade of the handheld machine we saw earlier?
Correct. So it utilizes the same X-ray technique, but this is way more exact. And this is OES, so optical emission spectroscopy. So in OES we can run some other trace elements that are very small amounts that we want to avoid. So this is basically looking for stuff we do not want in the steel.
Okay, so if things are popping up in here, it's a problem.
Bad news.
Something got in it that we didn't want.
Correct.
And there's the analysis from the XRF. Is it all good?
Yeah, so you can see that we're missing carbon still. So carbon is of course very important, but we cannot analyze carbon with the XRF.
So they now have to crush down a sample to be able to put it in the LECO equipment.
Correct.
Over there. In his hand there, that's a pot of powder sample from the Atomization tower, and that also gets tested in this lab. Okay, we are now one floor down.
So now we're looking at the ton dish. So we're actually standing on top of the atomization tower at the very top, and the ton dish has been filled with liquid steel. The ton dish holds the steel on top of the atomization tower, and it allows for a small stream of liquid steel to enter into the atomization tower. There it is in contact with two gas jets shooting supersonic nitrogen gas onto the liquid steel, disintegrating it into small steel droplets.
So effectively, the ton dish is that container of molten steel.
Correct.
You've dropped it down into the ground here, and then you're tapping from the bottom in a small hole where you're then blowing jets of nitrogen to atomize it.
Correct.
And turn the liquid into those tiny, tiny grains that are going to immediately freeze and solidify.
Exactly. And if we look outside the window here, we can see that we have two graphite electrodes that are actually going through the lid of the ton dish, and they're in contact with the slag layer sitting on top of the steel. Wow. So these are a measure to actually resistively heat the slag on top of the steel, keeping the liquid steel hot throughout the long atomization process.
Okay, so what's happening now?
They're opening up a small porthole in the side of the ton dish and the scoop to take out some liquid steel.
So they're going to monitor the exact chemical composition here and send it up to the lab like we just saw?
Correct.
Down we go. We're a few stories below. Check this out. That's the stream of atomized powder. How sick is that? We go down.
So we're at the bottom of the atomization tower. The powder is being collected here, then filled into canisters. The canisters are taken out. They're put into that rack over there, and then a forklift picks them up and transports them to the compaction unit where we're going next.
Wow, and that is the famous capsule, spiral welded steel. How thick is the wall on that?
3 millimeters thick. Yeah. The hipping will be done inside this canister. So the canister is filled with powder, about 1.5 tons of powder. Then it's welded shut and compacted in a hot isostatic pressing unit.
So this is functionally an identical process, but significantly more precise and clean. When I've made canister powder Damascus in the past, where I put, different types of powder in, I've even used 3D printing to make forms, to make pictures, and it's the same process, just on a way larger scale. And instead of hammering between dies or V-blocks to forge the canister down, here it is high temperature, high pressure gas environment that'll compact it into a solid piece.
Exactly, and that's the isostatic in the HIP part. So HIP stands for hot isostatic pressing. Isostatic just means that instead of hammering from two sides and then other sides, you're doing all of that pressure equally throughout all directions. Yes, and you do that by applying a high argon pressured gas into a vessel, basically.
And what's very interesting actually about that is this is, you said, a 3 millimeter wall on this pipe.
Correct.
If that was to be forged under dies, the wall on that pipe would need to be like 100 millimeters for it to just not burst all over the place. Because even when I make canister Damascus out of powder, I actually need like 10 millimeter wall steel for it to compact nicely and not make big voids where the powder then blows out. You don't have those problems with hot isostatic pressing because the pressure comes from all sides evenly. Correct. Thanks to that high pressure gas.
Correct. And there were actually trials before 1969 here in Söderfors with trying to forge weld powder in canisters, but it never worked out on a large scale.
The consistency just isn't there.
So they had to go to the HIP technology to be able to consolidate the powder.
And it was right here that that technology really found its legs. Yes. This is the beginning of a worldwide change in materials process to be able to make these materials consistently thanks to this hipping technology. Once those canisters have been filled, they are sealed and they are taken to this building.
Hello.
Hello.
Sabretta, welcome.
Thank you so much. It's lovely to meet you, and I'm so excited to learn about what happens here. Tell me.
Everything.
Yeah, exactly. Where does it start? You get this from the other factory?
No, the start is over there. We fill the powder and we welding and everything. And then it's come here and we cold isostatic pressing the capsules before the preheating furnaces.
These capsules
go
inside that tank of like a water-based emulsion.
Yes.
You put a lid on it. You then roll. Am I right in saying this is on rollers? That means that then you hopefully hold it tight because that's really strong.
It's very tight.
Super tight.
Yep.
And then you pump water in and pressurize it. Thousands of bar.
Yes.
And that compacts all the powder and gets it so that it's as tight as possible with as little dead space.
So the old capsules got a little bit smaller.
So you would notice a difference before cold isostatic pressing, and then afterwards it would be visually smaller.
A little bit.
Oh, that is crazy. And so they sit there, but it's not solid. It's just crushed powder.
Yeah.
The hot isostatic pressing is where it actually becomes a solid steel inside, and that's here.
Yep.
So from the cold isostatic pressing, they're then eventually taken into these furnaces over here. And this is the structure of the hot isostatic press. They're preheated over hours and hours, up to like 1,000 degrees Celsius, before, on train tracks, they're brought into this. That trolley has now moved across, and they're gonna load another capsule into the chamber. You can tell that's been seriously preheated. Now that the capsule is inside the chamber, this yoke gets moved over top of it to help support and seal either end. And you'll note that that yoke is basically identical to the yoke that supports and holds the ends of the cold isostatic pressing chamber. There's thousands of bars of argon pumped into a chamber where, with the hot argon and with temperature heating it, it forms into a solid. And it doesn't quite make sense to me. But when you put that capsule in and you pressurize the outside to those thousands of bars, without a hammer or an anvil, without a power hammer, without a press, it will compact it and effectively create a diffusion bond of the powder and turn it into a solid. After that capsule has been squeezed, it comes out the bottom of that chamber. So the capsule has now been lowered into the kind of transporting chamber and is now going to roll all the way back here to then be pulled out by that gantry crane. Out comes first a heat shield that goes around the capsule. Whoa! Down goes the clamp on this crane. Whoa! That's crazy. We're in R&D. This is the machine shop. I do love getting in nice workshops. Good stuff.
Nice to meet you, Alec.
Very nice to meet you too. Thank you very much for showing us your R&D department.
Yeah.
I love the look of this machine shop, but why does an R&D department have a machine shop?
Well, more or less you need to for two reasons. One of them is to prepare the samples while we're doing experiments or trials in production. But the second part also is that we're going to do delivery samples. You get pieces from the production unit, then you need to cut them up and be able to analyze them more easily by preparing the samples. Here, for example, this is from production. So we get these kind of slices from the billet line. And this is quite too big to be able to, when you're going to polish the samples to look at the microstructure, etc. So then we need to saw them up into smaller pieces that they're able to be more useful.
Okay. Is all the slicing just happening in this saw here mostly?
I mean, we have two saws, one here and one over there. These ones are mainly to cut up the larger pieces. But to be more precisely, we will use this machine right over here. We have a rotating cutting disc that's able to cut both soft and hard material. Okay. When I'm talking hard, we're talking upwards of 70 Rockwell.
Are you joking?
No,
You're cutting 70 Rockwell
we're able to do that, yeah.
Whoa! Oh man, that is hogging through there. This is probably an expensive abrasive disc for cutting 70 Rockwell steel.
It's not a cheap one, I can tell you that.
Yeah, I bet. Super nice surface finish. Oh, and you can see the jacket from the hipping and then the actual alloy they want to test in the middle. So the piece that we just looked at is an R&D sized test from the hipping, and it literally is made out of powder filled in a bit of regular steel tube.
Yep.
They crimp it, weld a seam, it goes in the massive hipping chamber on top of an enormous canister, and then ta-da, you can test and look at these samples and see exactly how things are looking on a much smaller scale without having to use 1.5 tons of powder. Ta-da! Anvil 3 of the day. So what are we looking at here?
So the theory behind this is that you're going to put a sample down towards where the hammer is going to fall down and hit and break the sample. This will be able for us to measure the toughness of the material by you looking at the difference between what kind of force you have when you fall down and then like when it comes up, you can see the difference.
Oh, thank you.
So this is a high cycle fatigue testing machine. So more or less what this will be doing is that it will vibrate at about, I think, 70 hertz. And it will apply a force of between 30 to 70 kilonewtons every time, 70 times a second.
So there's a hydraulic cylinder beneath this that is now vibrating 74 times times per second with 3 tons of tension on the part. And after how much time is this likely to break?
I mean, it depends, can take a few minutes up to a few hours. So here's the one of the dumbbells. So
that's machined here on the shop floor?
Exactly.
That's what you've got that Swiss lathe for?
Yes. So we have sort of like a waist right here, and this is where we want it to break specifically. Here we have a broken surface of the material, and you can actually see a white dot. It breaks always at some place, some defect, etc. So this is where it actually starts to break in this fatigue test and just grows out.
Okay.
And it's also a good way for us actually to find inclusions in the material too.
And that little white dot might be, for example, a little tiny inclusion that the crack then propagated from.
Exactly, and this makes actually being able to identify what kind of inclusion it is and actually measure it in our scanning electron microscope that we have.
So you'll then take this to the scanning electron microscope, you'll find that little white dot, and you'll go, oh, this inclusion is...
Yeah, X, Y, or Z, and we actually find where in the production it has occurred, and in that way we can actually avoid it more and just work to reduce the amount of inclusions inside the material. So this is a continuous improvement. So here we have it. This is our scanning electron microscope. This is a piece that I've prepared. It's a powder, so we placed in a holder in here.
What?
So this is a big thing, because usually when using light optical microscopes, you're limited to about 1,000 times magnification because light becomes too big. So instead you need to use electrons to actually get a higher magnification. So
you're blasting electrons at it, and then effectively, you know, looking at what reflects back.
Yes.
But light would be too big.
Light would be too big. I mean, light is about 400 to 700 nanometers. And here we have 2 microns. So I think a fourth of this is about 500 nanometers. So we're going to try to get actually a good image. Focus.
Oh, you're focusing it.
Yeah.
Dude, that is crazy.
So about here you see particles that's larger than the, color blue.
Wait. We're looking at particles that are larger than the wavelength of the color blue.
Yeah. That's the magnification we get. This is 17,830 times magnification.
It looks like we're looking at the surface of Mars. That is incredible. We're looking at steel powder.
So we're going to now measure on the point to see like what kind of chemical composition we do have here. It's going to take some measurements.
And here on the screen, you've seen carbon, vanadium, chromium, iron, molybdenum, vanadium, chromium. Incredible. Thank you so much for sharing with us what you do, man.
My pleasure.
This is a great privilege. We are now headed into the billet line. The powder has been atomized. It has been pressed together into a solid billet. And it is then time to go here, where billets get forged out in a GFM. I don't know what that is, but we're about to find out. Okay, so this is the forge shop. Wow! Oh, I do love a good forge shop. Why on earth, Victor, have we gone to the effort of turning the scrap steel into powder to then turn it into a solid to then forge it down? There's tons of... we've seen steel made at Tata Steel.
Yeah.
They just pour it out into an ingot and they forge it out.
Yeah.
Why the powder? What's the story?
Well, there's several benefits to making a powdered steel. First of all, we make a very highly alloyed product. You wouldn't actually be able to make most of the grades we make without making it into powder first. If you try to ingot cast these highly alloyed grades, the problem is that they will basically disintegrate when you start to forge them because there's so much segregation within the steel. You have all the alloying elements pooling together and forming clusters of carbides that make the steel, or the ingot in this case, extremely brittle. But when you make it into powder, you get such a fine distribution of all the alloying elements within the steel, so you sort of regain a lot of that toughness into the product, and you can actually forge and hot work it.
And so, for context, when you say highly alloyed,
Yes.
in my workshop,
Yeah.
I'll work with sometimes mild steel, 0.2% carbon. Sometimes I'll make a knife out of 0.8% carbon.
Yeah.
Sometimes I get bold, there's 2% nickel in it as well. But largely, I've got like 98+% iron in the steel that I forge.
Yeah.
When you say highly alloyed, what do you mean?
Well, it's basically the highest alloy steels made in the world. So, I mean, we're talking about up towards 30% alloying elements, 65% iron for the highest alloyed grades.
And so, 30% of that bar of steel could be materials like tungsten, vanadium, molybdenum,
Cobalt.
cobalt.
Yes.
And that's just not conducive to traditional steelmaking techniques.
No, if you try to make that through ingot casting, it would never work, basically. So you need to do that to refine the microstructure. Then, of course, it also brings other benefits. The material becomes more tough. You can also hot work it less, because with a conventional ingot casted material, you actually need to hot work it to break up all those carbides within the steel and refine the microstructure. We're actually starting with something that is already refined from being a powder. So we have very little need for the forging from a refining standpoint. We do the forging and the rolling just to work it into the shape that we need for selling it to a customer. But it's not doing a lot for refining the steel in the end.
So what is different in how your molten steel alloy turns into a powder as compared to when your molten steel alloy is poured into an ingot mold? What's different about how that works that means that you get a better result from the powder than you do from just letting it cool in a big bar?
Yeah, it's all about the solidification time in this instance. So if you're making an ingot that are several hundred kilograms large, it takes 30 plus minutes for it to solidify inside the mold, the ingot mold.
Okay, so it's going to be going from liquid to solid over that time.
Yes, and it gives lots of time for diffusion to happen, which means that alloying elements will clump together and form these stringers and large carbide networks that we want to avoid. In the powder process, we're basically making tiny ingots at a fraction of a second. So it goes from liquid steel to solid in less than a fraction of a second.
Okay.
So there's no time for diffusion to happen, and all of those alloying elements are locked in perfect dissolution throughout the steel. So there's no diffusion happening, basically. All the alloying elements are perfectly spread out in the steel.
Okay.
Yeah.
So this allows you to make sure that long carbide stringers don't become a stress concentration for cracks to form.
And that's perfectly correct. Basically, you are alloying the steel in such a way to get carbides. So you actually want the carbides in there. But when they clump together and form large, massive carbides within the steel, they become a problem.
Okay, so it's about forming the perfect carbides thanks to these high alloying elements, but forming them the perfect size and shape every single time, the whole way through the bar.
Exactly. And with conventional steel making, you can achieve that by a lot of reduction. So when you forge it out, you can actually start to break down the carbides into smaller, rounder carbides and get a very even distribution throughout the bar. But you start with a cross-section that is, you know, similar maybe to what our capsules are, which means that you need a certain amount of reduction ratio to actually hot work the material through with a conventional steel making.
Whereas here, you can have your capsule like this. It comes out of the hot isostatic press. You can slice it off and you could make something from it at that stage without needing to do that reduction as you would when you make a traditional ingot that then needs to be rolled down a significant amount to stretch out those stringers into something consistent through the whole bar.
That's absolutely correct.
Okay, so let's go see how they forge down these now solid capsules into round bar. Oh, even better, we get to walk through the maintenance room. That's a big milling machine. That'll cut some steel.
Hello.
Hello.
Patrick.
Great to meet you. Thank you so much for showing us around. I'm so excited. So where are we right now?
Right now you're in the maintenance department.
If you want, we can have a look at the forging hammers.
Oh, I'd love to. Are these the dies?
There's different dies. These are for flat and square dies. One set, and this is the normal set we do for the round bars. Cut it out and gonna weld it up.
Right, so you're gonna rebuild it up because this has been worn down. How often do those forging dies wear out and need to be fixed?
About every third week.
Every third week? Wow, that's a lot of maintenance. That's endlessly, there's an endless cycle of needing to fix the things because, well, in forging, all the machines are trying to break themselves at high speed. We're headed into the billet forging room. Oh my goodness.
So this is the forging machine. So the 4 hammers working together.
You've got 4 hammers hammering constantly as you rotate the bar around. God, you can feel the ground shaking from in here. This is amazing. And you've got these incredible camera views showing it happening. And so you're forging all the way around. You know, in my blacksmith workshop, when I'm changing the cross-section of a bar, I'm always thinking about changing it in square cross-section or in hexagon to make sure that I don't get it kind of ripping apart. Here, with these 4 hammers, you can work 360 degrees, spinning around as you go. So that's a video feed of a capsule going into the furnace. Damn, that's cool. How long will that capsule take to heat up?
4 hours, I think.
4 hours? Does it still have some heat from the hipping?
No, it's been in the preheating furnace.
Okay.
Up to 800 degrees.
Got it,
Yeah.
got it. And these furnaces, these are electric furnaces?
Yes.
Okay.
This is the high temp furnace.
Oh my goodness. And so each color represents one bar that's in the furnace being heated at the moment?
Yes.
So you've got dozens of bars in the furnace at each one time?
Yes. And this is the low temp furnace.
Wow. I presume every single grade of steel you need to forge at a different temperature,
Yep.
and you might be forging different grades one after the other. How do you manage keeping track of that?
Just by the zones.
And you just keep track of where each billet is and try not to get it too hot, try not to get it too cold. So this is your GFM forging machine. And when the material comes out of the hip, it's 410 millimeters in diameter, 1.5 tons. In one heat, what diameter will it be?
Down to 110 millimeters.
That is incredible. They're taking a bar like this and taking it to that in one heat. And you have 4 hammers striking simultaneously and rotating it from these heads at either end. The material is supported here in the middle so it doesn't bow. These jaws are clamping it and rotating it through 360 degrees. How many tons of force are being applied by the hammer each blow?
I think up to 900 tons.
900 tons! So this has been forged out, it gets pushed over to the next line.
Yeah, and it's going to be cut over here.
Oh, it gets cut! So good. So good. And you can see the characteristic fish mouth at the end.
Yeah.
Much the same when you work a bit of steel by hand, the end, when you change the diameter, fish mouth's over and you always have to cut it off.
Yeah.
Amazing.
We call it a pipe.
You call it a pipe?
Yeah.
Okay.
I used to work in an open die forge before.
Oh, you did?
Yeah.
Oh,
For
amazing.
30 years.
Oh, that's incredible. What sort of hammers were you using?
No, we had an air hammer for 4 tons.
Yes?
And we had a press for 1,000 tons.
Amazing.
Yeah. And
Oh, so
a
you've been-
manipulator for 6 tons.
Amazing. So
Yeah.
you've been involved in forging steel for a long
Yeah.
time?
Since I was 18.
Amazing. Incredible. Beautiful. I could watch this all day. I would never get bored of seeing this machine work. So after the GFM forging, the bars are trimmed and then loaded into this furnace here. This is a side-loading furnace. These doors will lift up, the bar will roll out, and it'll then be fed down this line into the rolling mill, where they can then really change the diameter and significantly improve the surface finish. And it rolls back and forth. Amazing! Oh, yes! These are the feed rolls, and then to the right are the proper beefy rolls that really change the diameter. This cassette has multiple sets of rolls, and you'll see that after each pass it moves. Because the material's got smaller, it needs to move it to a different set of diameter rolls. So this means instead of having to have one enormous long rolling mill line, they can push the material back and forth, progressively reducing the diameter, creating a really improved surface finish, and all they got to do to change diameters is change that cassette unit. You'll see that that one over there makes 105 millimeter and 85 millimeter bar, and it does it pretty quick. So really efficient, space-saving rolling mill compared to what you'll see in a normal steel plant where it might be hundreds of meters of rolling mill. It's probably absolutely perfect for a plant like Eersteel because they're not an enormous mild steel producer, producing miles and miles and miles and miles of material every day. This is a niche product for a really specific application. They need tooling that's modular, that can have quick changeovers, because right now they might be making this bar, but this morning they might have been making a different diameter of a different grade, etc., etc. Once that bar has been back and forth here, it goes down this line, and while it's still hot, it gets cut to length. That saw cuts off the ends to remove that fish lipping defect at the end, before the bar can then move towards annealing. Right, we are now headed to go see the finished steel. Here's the surface finish of the GFM. You can see there's a few flat spots because it's hammered between those 4 flat dies. After it's been through the rolling mill, it's a much smoother diameter. It's then ready to be annealed before final turning.
This is the big one. Here we do from 125 up to 330.
In this lathe?
Yes.
Oh yeah, I bet that lathe has some horsepower. You're joking, so all your products of that dimension literally get turned right here on a manual lathe. Yep. Is it a fully manual lathe or is it CNC?
It's controlled by...
Okay, it is CNC. Kind of partial CNC?
Yeah.
God, look at the size of that.
We have a big CNC waiting to be installed. So.
Gosh, look at the size of the insert compared to my hand. It's enormous.
We have 2 kinds of annealing too. We have a step annealing furnace there, and we have a soft annealing furnace in there.
What is the difference between the two?
The difference is more controlled cooling in the soft annealing.
Okay.
So all the bars go through soft annealing, all the billets go through step annealing.
Okay, got it. And the difference between bar and billet is the bar is finished diameter. The billet still might have some more forging.
Going further to the next shop.
Okay. So you need a less precise annealing for the billet than you do the bar.
It's going to be heated directly. So.
Exactly. So it's just to make sure it doesn't crack.
Yeah. So this is the peeling machine.
You're joking.
Yeah, no, man.
Oh my gosh. You got to see these inserts. So the peeling machine has 4 tool holders like this with inserts. Incredible. This has got some weight to it, doesn't it? Do you know how expensive one of these inserts is?
I know, but I'm not going to tell you.
And so this is the surface finish, obviously, off of the rolling mill.
Yep.
It's been annealed, it's been straightened, and it's now going to be peeled. And how does that machine work? It's got 4 of these tools.
And the tools spin.
The tools spin, the bar doesn't.
Yep. That's right.
Incredible. These rollers feed it through the machine, and then on the other side, just like that, it comes out with a turned finish. And that's the surface finish of a finished bar, ready to go to the customer, ready to be turned into all sorts of things. Ready to be made into drill bits and machine tools, ready to be used in aerospace applications, or ready to be used in tooling for forging axes, because Granthurstbruk uses steel that is made here for some of their axe forging dies. The things that this material will be a part of producing around the world are endless. An enormous thank you is owed to Eersteel for letting us visit and see how they do it, learn about powder metallurgy and bring you along. Thank you so much for watching. See you on the next one. Bye-bye.